Yeah. Okay. So early in my career, I hadn't been converted to the Church of Bays yet. But I had learned about these hierarchical models or mixed models, mixed effects models, as I knew them as back then, and used the tool Elmer in R, but quickly found that it was for the kind of nuance and complexity I needed to kind of have in my models. The maximum likelihood kind of estimation procedure was very fragile. I could kind of demonstrate to myself it was not converging or converging on things that made no sense. So that was kind of my first impetus to search out alternate things, and became quite happy to discover Bayes and the kind of the regularization that priors can provide, that extra information to pull us away from extremes of the parameter space, but then also the fact that it's doing something different in the parameter space. It's not really searching for a maximum. It's actually just trying to establish kind of a kind of region of the parameter space that actually maps much better than kind of frequentist stuff does to the things that we want as scientists. So I come to this mostly as a scientist, where you have kind of questions of interest that you then try to kind of tailor your models to address. But then often, as discussed in the earlier session about workflow, you discover new things about your data that speak to what the generative process is. So often you have some core questions of interest, and then your data speaks to other questions or other kind of nuances you hadn't yet appreciated. In kind of my world of modeling of cognitive science, brain processes, the idea of a hierarchical model really is maybe only about 15 years of prevalence. We started getting, around 2008, some big papers in the methodology journals talking about how the inferences that you would derive from traditional approaches, where you have hierarchically structured data, but then you ignore that hierarchical structure, you compute some descriptive statistics, and then you proceed with inference from there, would lead you astray. And people have started to really come to hierarchical models. But there's a lot of useful tools for kind of fairly automatically looking at these models. So BRMS, for example, has the Elmer-like syntax, much more flexible and much more nuanceable. But I tend to still be like a Stan primary person. Partly I haven't taken the time to learn the extra nuances that the BRMS syntax provides. But I also just like the confidence I can achieve by seeing exactly like the operations, the transforms, etc., that are happening in the code itself. But to start us off, I actually wanted to start off with to go over some principles that are going to repeat in a non-hierarchical context. I missed the last half of the intro session, so I'm not sure how much this is going to be redundant, but redundancy helps in coding. So there was another thought. All of this stuff. I have a GitHub repo that I'll be putting this up to. So I'll also say that the first little bit is fairly prepared, and then I got quite ill last week, and so my bandwidth for actually getting this to be a nice sparkling presentation was rather limited. So we'll transition probably fairly inelegantly to a little bit more of an interactive workshop style here. So starting off with the I wanted to make few assumptions about background. So I always hated when I was first learning things to start out with coin tossing. I've now, having taught a few times, discovered that actually that is a fairly useful, simplest type scenario. So I'm going to sit down here. So we'll start out with Bernoulli outcomes, and then we'll transition to Gaussian outcomes, which are more interesting and have at least some aspects that will generalize to other kinds of outcomes. We've got a model here, very short, terse model of, again, non-hierarchical. As data coming in, we've got just a vector or array of ones and zeros. So the results of flipping a coin, for example. Over here, actually, there's like a little diagram, something I'm working on, something that is actually I discovered is already in tools like PyMC3, but the ability to take a Stan program and turn it into something that's like a directed acyclic graph. I more think of this as a dependency graph with the type of variable that we're talking about as the different colors. So you'll always see this legend over here. And the way it's structured is like in the generative format. So, oh, go ahead.
Sorry, could you make it a little bigger?
Oh, yeah, sure.
Oh, that's beautiful.
Okay. So generatively, the way this model works is there's this parameter here, probability of success. It's bound as to 0 and 1. We've put a beta prior on it. So if I recall correctly, let me actually just say curve d beta x 1 1 from equals 0 to equals 1. Flat. There we go. I guess I always so flat prior. Something that I'm trying to undo to myself. Often with parameters, it's usually a good idea to put an explicit prior on a parameter. I got into the habit for parameters where I wanted to be truly uninformed about them. I'd omit the prior on that. So if I had this model and I just took out this line or commented it out, it would have the exact same log probability. It would have the exact same behavior, but now that I've started doing these graphs, I actually like to have that prior in there because then it really shows in the graph what's going on. So we've got this beta distributed distribution here that if you think of things generatively, like we're actually generating samples from this model, that determines a sample for what the probability of success is in a given kind of iteration of the model. And then that probability of success is then a parameter for a Bernoulli outcome, something that's either 1 or 0, and that determines what a given observation is. Here, the observations is a collection of things. I want to update this to make it like plate notation so that you have multiple like observations, so from 1 to n, but that's down the line. So very simple model. The kind of nuance that I'll introduce first is that we're fairly used to thinking about probabilities, even though humans actually aren't very good at doing probability comparisons and that sort of thing. Something that's a little less intuitive but more common in more complicated modeling scenarios is to not talk about probabilities as this bound to 0 to 1 thing, but talk about the log odds of a success. Say heads we'll call a success. The model for this is fairly similar. Here I've got just like highlighting what the changes are. So the full code is there. I've got like little dots indicating things that are not changed. So here what has changed is that instead of a parameter about the probability, now we've got something that's unbound and it's the log odds of success. This prior means something different than the prior that I had before. I had a beta 1, I had a flat prior before. I guess if I just left off any prior, that would be equivalent to an unbound prior, but it's particularly with unbound variables, having no prior or a flat prior is fairly pathologically, or it's likely to induce pathology. So here I use a different prior, standard normal. That tends to put lower weight at the extreme probabilities and higher weight at the middling probabilities. If you had real data, you'd want to adjust this to what your actual priors about that kind of data would be. And the only other change there is that instead of up here using the Bernoulli kind of expression of what the distribution of the observations are, you're using the Bernoulli logit. So that knows about that it's a transform from this log odds scale to a 0 to 1 outcome. So pretty kind of trivial change. It does mean that the thing that we're doing inference on, the log odds of success, is maybe something different from what folks that are familiar with probabilities would be used to. You can always transform from one to the other pretty easily. But what it does is that it enables us to, it enables us to do more complicated things without having to keep track of, with probabilities, again, it's a bound variable, so you can't, it's harder to do regression in a bound context. You'd have to keep track of, okay, if I have a regression beta that pushes things above 1, what do I do with that? So log odds, it's just much easier to have to import the kind of linear regression tools that folks might be familiar with into that context. So this is this next example is just a model that shows similarly a binomial or a Bernoulli outcome 1 and 0 as the observation. We're using Bernoulli logit as the kind of next step above the generating that. But now instead of a single parameter that determines the outcome at a given or that determines the log odds of success, we actually have a regression structure. So if I scroll this out, does it expand? No, it doesn't. So it doesn't matter how zoomed in it is. We have the standard kind of simple linear regression formula where you've got some sort of intercept, and then we've got some sort of beta, and then some sort of other data variable. I've named the data variable up here, time of day, just some arbitrary variable that you're measuring. Time of day actually might not be good because then you'd expect some sort of cyclical phenomenon because time of day is a cyclical variable, but I guess ignore that for now. So with that regression context, you need to have 2 parameters here, an intercept and a beta. We could actually collapse those into a vector of 2 elements, and we'll have some examples of including the intercept as a quasi-beta in a little bit. But here I just wanted to keep them separate to really highlight that this is kind of standard single variable regression. And again, this is all kind of just making sure everybody's on the same page in terms of, okay, we know what kind of regression would be and before we hit hierarchies. This is an example of like a single regression where you have one variable that's continuous and you're trying to assess the influence of that variable. Again, the intercept is talking about the is about regardless of what the value of this variable is, where is the overall mean of the data. Except that depends on what I've done to this time of day variable at the outset. If I've literally called, okay, midnight is 0 and onwards, then the intercept is literally what is happening at midnight. Whereas if I just had a sort of random distribution of time of day measures, the intercept, and I did what is standard, which is to center and scale the time of day variable, then the intercept would reflect what is the mean of all these time of day measures. What is the implied log odds at that mean time of day? I won't go too into this, but a general kind of good practice is to, as long as you can wrap your head around what has changed about the interpretation of the intercept, it's usually a good idea to center and scale your predictor variables. That puts things closer into the range of the kind of initial values that Stan will start out with to make those beta parameters a little bit more easily able to find. But it does then change what these priors imply. So if you've scaled something, then you probably need to change what your representation of the prior is. Did he go through prior predictive checks? I saw a nod and I saw a shake. So he did do a posterior predictive check. Okay. Let me put that off till a later thing. We'll actually code up that prior predictive check, because that's part of the workflow. We actually had an original design of things, and I think Mitzi, are you gonna go over prior predictives through BRMS? Yeah. Okay. So Mitzi will show how BRMS does the prior predictive, and we'll code up something that's a little bit. Once we get to the hierarchical stuff, that's where prior predictives become increasingly important, and I'll go through that process there. But the gist for now is that if you do any kind of scaling, if you set your priors dependent on like a absolute interpretation of your variables, and then you rescale your variables, center them, etc., you then have to go back through your priors and make sure that they still generate data that makes sense, that your priors are actually encoded properly by the formula that you put in there. That's single regression, single variable coming in. There's not a lot that's different about going from a single variable regression to multivariable regression. We've got a slightly different kind of diagram. So this is the single variable regression. So intercept and a beta here, and this is the data variable coming in of time of day. Here it's fairly similar. In fact, we have intercept and beta and some data variables coming in. But if we actually look in here, and if I had proper plate notation, we'd see it automatically. Whereas up here, the beta was just a single real. Down here, the beta is now a vector. So we can have any number of predictors encoded. So up here, I think we had n obs as the number of observations of that variable. Here I've changed it to number of rows in a matrix, and n calls is the number of variables. So instead of a vector with a certain number of rows, we now have a matrix with a certain number of rows and a certain number of columns. So we can still represent a real as what the intercept is. That becomes even more nebulous now. It's about what the kind of prediction is, or what the implied log odds of success would be when all of the other predictors are at their 0 point. Again, in using this sort of regression, you usually want to scale your individual columns. I come from mostly an experimental context, so we usually do a lot to make sure that our predictors are orthogonal with regards to one another. People coming from a more observational context would have the possibility of your predictors tend to covary, have a correlation amongst them, and that is something where you'd want to. That can cause some issues with how efficiently the sampler goes. There's some tools in the Stan toolbox to account for that kind of collinearity in your predictors. QR decomposition is a keyword if you want to look at that, where you can basically take your correlated predictors, transform them, have Stan do inference on the transformed predictors, but then get back out what that implies for the untransformed predictors and their relationships. But that's not an area that I have a lot of expertise in, so I don't talk about it that much. But the actual linear model, so again, we just have an intercept, and this beta here, even though we've got a new variable, new kind of variable, above we had a real that was expressed as having a normal distribution, standard normal distribution. We now have the same thing on the left-hand side, so we now have a vector, and we're able to just write it the same as before because the Stan folks were kind enough to make it so that it automatically knows that the vector on the left-hand side means that it applies the same thing on the right-hand side to every element of the vector. So in this, these are kind of independent. It's going to express a model that reflects independent priors for and independent samples for each element of that vector beta. And then finally, I've expanded it out to more lines. I tend to like to use white space as kind of make things a little bit more human readable. But we have the same kind of thing up here. We've got an intercept plus something. So a beta and then multiplied. Actually, here, quick question. Does anybody know what it means to have the dot star? Okay, so yeah, element-wise, it's an element-wise multiplication. In this context, it means in this particular model, since the thing on the left-hand side of the dot multiply is a real and the thing on the right-hand side is a vector, it has no, I could have put just a multiply there. I've gotten into the habit of putting dot multiply intentionally whenever I want to have an element-wise multiplication because I've been burnt too many times by forgetting that usually multiply in Stan is matrix multiply, and if you happen to have a vector times another vector, or vector times a row vector, for example, it will give you a very different result than the element-wise multiply that I, coming from an R world, tended to expect. So here it didn't make a difference. Down here, we're not even going to use the dot multiply. I also am not great at matrix multiplication, and I have subsequently realized that this last little bit, this stuff in this bit, is actually, I could do a matrix multiply. But should I actually do that? I do it later as a matrix multiplication, so I'll leave it as is here. But the general idea here is that we've got a single vector that's betas, and we have this input data that's this X predictor matrix. And what we want to do is take this vector and multiply it by each of the kind of rows in X. Because again, as I described it to you, the predictor matrix has a bunch of rows, but each column is a different predictor. So this vector of betas needs to be kind of rotated, multiplied by each column, and then the last thing with regression is that you add them all up. You have the intercept, but then you also add up the contributions of each beta times each column that is in that predictor matrix, or that predictor row. So that process of taking two vectorish type things, or a vector, two vectorish type things, and multiplying them element-wise and then summing them up, that is a dot product. A while ago, I discovered that because of how Stan stores the things, there's actually quite a big difference between taking the data as is, as the predictors in the columns, and leaving them as such and doing a rows dot product. in which case I actually have to have this beta as a row vector. It's actually much faster to actually transpose the data so that the thing that you want to kind of iterate over is over columns, because we want to do the same thing per row. So that's why I have X transpose here, and that beta is a vector now. So now we've got two matrices where we just want to do a dot product of this one's is just one column, and take the first column from this matrix, dot product. Second column from this matrix, dot product. So that's why columns dot product is there. If I were smarter, I would have realized that I could have just done a matrix multiplication here, and it would have given me the same thing, which is for every row in this matrix X transpose, it would have given me the value that reflects the dot product of the vector and the matrix input. We'll see that in a little bit later. So I wanted to go through those. First, okay, simple kind of generative model of Bernoulli data, expanding that or transitioning that to from probability to log odds, that we can then introduce regression. And then furthermore, this idea of multiple regression, you start dealing with matrices, and that has some complexity that clearly I've even still have yet to encode properly myself. But the next little thing that before we get to, before we transition from Bernoulli to Gaussian is a performance tweak that is available for both Bernoulli outcomes and as well Gaussian outcomes, that for these simple models is not useful. But as you get to more complex and data voluminous hierarchical models, it's going to be very useful. And that's something called sufficient statistics. So in the context of Bernoulli models, it turns out that way up at the top, I guess, I'll go back up. We had the input observations were just ones and zeros. And we had a bunch of them. It turns out that if you know the number of ones and zeros and that you have, you can get the same information content by actually just collapsing that down to what the count of ones is, and then what the total number of attempts that you made. So that is just the probability, the empirical probability. So that's what the sufficient stats for the Bernoulli does, is it simply takes our number of observations that we had and simply asks, okay, and how many of those were ones? And now instead of having I guess I should clarify that up here when we have on the left-hand side, this array of multiple elements, technically this is going through and doing as many operations as there are elements in that array. So it's doing n operations. Whereas down here, if I have simply the number of successes, that's a single number on the left-hand side, there's going to be a single number on the right-hand side, and so it's a single operation. So we've now reduced the number of operations fairly dramatically depending on the size of the problem. Here, the difference is, because the model is so small and likely to be, well, I guess if you had n-obs as very large, you'd maybe notice it, but probably not. But this will become useful for the larger models, and so I wanted to introduce it before we had the complexity of those larger models. And I think I've got some examples here where it just modifies the previous regression and multiple regression to talk about this, to have instead of the data as the individual observations as one and zeros, to have it as the sufficient stats. I'm trying to remember whether there was much in the way. Oh, right. So if you move to regression, and this is actually important, again, you've got this idea of time of day, and the idea here is, and it'd probably be best to put this in concrete terms. So let's imagine an experiment where at a given time of day, and you flip a bunch of coins. So for a given level of time of day, you have a number of observations. So you have some set of time of days that you've observed. And for each of those time of days, so that's why we have an array of size time of days, you have some number of observations. Maybe they're all the same. Maybe you did 10 flips every time that you did a time of day measurement. But maybe that varied. So you have a count of the number of times you flipped, and then also a count of how many ones you got. So you now have like slightly kind of different data coming in. But then the only other thing that changes is the last likelihood thing. Similarly with multiple regression, again, the thing that's changed is now we have the number of observations as an array coming in and the number of successes as an array coming in. And that's going to be unique to every kind of combination of, for every row that you have in your predictor matrix, you have these summary stats, basically, of the observations that are associated with that row. And then down here, the only thing different about this expression of the likelihood is that you're using the binomial logit. Like everything on the inside is, particularly this expression of the regression, is the same as before. I haven't been pointing to these, but they're fairly trivial at this point. Going to Gaussian outcomes, there's not a whole lot that's different. With a binomial outcome, there's one parameter that determines everything, the probability of success or the log odds of success. With a Gaussian outcome, there's actually two parameters that could be of interest. You've got where the Gaussian is located, as well as the scale of the Gaussian. So what is the scale of measurement error? Here we're talking about specifically the likelihood, so interpreting that scale parameter as a kind of magnitude of measurement noise is what I usually like to do. So we have, when we dealt with binomial data, we had to talk about ints. With the Gaussian data, we can talk about reals, which means that we can, instead of having an array of reals, we can just have a vector. That's a kind of convenience that the Stan language has. So we've got a vector of observations. There's n obs of them. And instead of having a single parameter that we're interested in this simple non-regression case, we've got two parameters, one that's a mean and one that's a standard deviation. I use mu and sigma here. Usually I like to be a little bit more verbose in my parameter naming, but for something this simple, I went with what is fairly standard in terms of naming. And critically, as you probably saw this morning, we can express parameters having bounds on them. So the standard deviation, you can't have a negative standard deviation, so it's a lower bound of 0. In terms of priors, of course, you'd want to modify this to suit whatever the context you have. That can be done either by literally modifying the priors that are expressed down here, or you can just rescale the data so that these priors make sense. I tend to do that latter. That way I can kind of reuse the same Stan programs over and over. But here, this is expressing a prior where the mean is kind of centered on 0 with a standard deviation of 1. And then the sigma, I use a Weeble, which is not super common. Often you see people use a sigma, a prior on a standard deviation that's, again, another standard normal, so peaked at 0. I think it's rare that we actually have measurement contexts where we believe most that our measurement is noise-free. So I like to have expressions of at least the measurement noise that is not peaked at 0, has some sort of ramp up, and a Weeble has a nice, let's say 2, 1, and 5. Has a nice like ramp up shape. It's kind of like a log normal. Log normal actually has a thicker tail, which I find is a little unrealistic. I think there's some other distributions that are very similar to the Weeble, but Weeble is the one that I knew of, so that's what I tend to use for that measurement noise. And you'll see that a few times. In a little bit, we'll actually switch it to something different. But then the likelihood is fairly trivial here. You've got the observations expressed as having a normal distribution with a mean of mu and a sigma and a standard deviation of sigma. So that's pretty simple. Extending into a regression, if we had a regression, a very common thing is to look at, to kind of be most interested in the effects that our variables, our predictors have on the location of the normal distribution of what we expect, kind of, what we have as the expectation of the measurements. So oftentimes people just put aside the noise parameter and have that as a fixed thing. I think if I have my full code over here, I leave sigma as a single kind of variable, and then I have two new variables instead of a single mu. Now I have two variables, a mu intercept and a mu time of day beta. So similar as with the binomial case, now we're talking about an influence of time of day on where that kind of central tendency of the data is going to be. We've got down here in the now some priors on those things. We've got the regression equation here, but sigma is, again, this fixed thing. That is super common, and it can hold in a lot of cases, but I've increasingly moved to what are called location scale regressions. And that's where you actually have influences of your predictors both on the location of the observations, but also on the scale of measurement noise. There are some cases where there's like known effects where the measurement noise like directly correlates with where the location is. So that's usually better captured by doing like a log normal type model. But in the context of just not having any strong prior information that noise definitely doesn't vary according to your predictors, but then also not having a strong prior that it's a perfectly like kind of log normal scaling, I consider it better to actually just keep them separate. So I'm actually going to pull up the full code over here. So we've got the mu as before. We've got an intercept and a beta. We also have this new thing, eta, and it has an intercept and a beta. So eta is just my own random Greek letter choice for talking about log variance. Just like when we had this transition from probability, which is a bound variable 0 to 1, to log odds, to start using these tools of regression, with the bound variable of a standard deviation not being able to go below 0, it can be more useful to talk about to transform to an unbound scale so that you don't need to kind of keep track of how close to the bound you are. So in the world of people that model these location scale models, the log variance tends to be, we could do log standard deviation, but that tends to have, in terms of whenever I run my prior predictive checks on those sorts of things, I have a lot of trouble getting out reasonable predictions from standard models that I don't know, accord with my expectations, whereas log variance tends to behave very nicely. So that's what I call eta, is a log variance. That means that when you get down to the normal expression, we need to get to a standard deviation. So to undo the log part, we exponentiate, and to get from a variance to a standard deviation, we square root. That adds a couple operations, but for the clarity of getting a nice way to express priors on things, it's still worthwhile in my kind of, in my opinion, to talk about the log variance as the core kind of parameter of interest. But not a lot has actually changed from looking at just location to a location scale. All we've done is added these extra parameters. The mu parts have all been identical. It's just this talking about what's happening with the measurement noise part that's different here. And with multiple regression, I'll just it's the same thing. You just have etas now, and an intercept and a beta with the etas, and in the same way that you do this columns dot product, that really should be just a matrix multiply. For the mu's, we do the same thing for the etas. Critically, there's no real implied relation between what, say, the mu intercept is and what the eta intercept is. There's no kind of tying together. And they're actually, I guess, I can't think of a realistic model for it, for talking about the betas as having a correlation in some way. You could do it, though, and we'll get into examples where we are having that kind of correlation between the two kind of pieces of, I guess, the two regressions that you're doing. But here, things are just independent. Those are two independent things in your model. Before I go on to the Gaussian sufficiency stats, I'll maybe pause and see if there's any points of clarification or points of confusion that anybody has. I know it's always awkward to ask those, because then you're asking people to admit to not understanding something, but I feel that
When you are specifying the prior standard normal with the parameters, what does that do in standard?
Okay, yeah, sorry. I was somewhat assuming some content from earlier. So standard normal is just a normal distribution with mean of 0 and a standard deviation of 1. So it's the actual expression is very fast, and the computes in Stan and the autodiff stuff have been made very fast. So I like to kind of rescale my data so that whenever possible I can express a prior as a standard normal.
I think you might have touched on this now, but the same model is just doing normal 0, 1. Did you say that this function itself is optimizing?
Yeah, precisely. Yeah. So I could have written that as, instead of std underscore normal, I could have put normal and then in the parentheses 0, 1. It's just that in terms of compute, standard normal goes faster. With these simple models, you're not going to notice a difference. With more complex models, you would start to notice a difference between just in terms of how long it takes to compute. You're not going to get any accuracy differences or anything like that, just purely compute time.
Also the case if you just have this unknowns over a few parameters, or is it the case that you have millions of parameters? Is it then that
Yeah. If you had lots and lots of parameters, you would start to see different, and that's I guess what I kind of mean by the more nuanced, more complicated models.
But not in the cases where you have a few parameters. But
Yeah. All right. So the sufficient stats thing. So I talked about sufficient stats for the Bernoulli outcomes, and that is in the Stan user's guide already. And there's in fact that built-in Stan function Bernoulli logit. I said. Let's see, what was it? I always get Bernoulli and binomial mixed up. Binomial logit is the sufficient stats thing that you can use too. There's also a binomial if you want to have inside as your kind of parameter in there as being probability. But again, I almost never use that. So I always use binomial logit. So there is an explicit binomial logit function in Stan that is the sufficient stats version of the Bernoulli logit. There's no built-in thing for Gaussian outcomes, but there is actually an expression that is a sufficient stats expression. It turns out that if you know how many observations you've observed, and you know what the mean is, and you know what the variance is, those three pieces of information give you all the information you need to talk about even a collection of normally distributed samples. So in the same way that knowing the number of observations you made and the number of successes entirely determines the probability that is pertinent to doing inference on the probability of success, knowing what the empirical mean is and the empirical variance, as well as the number of observations, entirely determines the information that you need to do inference on the parameters of the mean and the variance for those. So to the simple, there's actually, so if we, in the repo, you'll see that there's a functions.stan file. If we look at that, there's an expression. So if we have this vector called obs, and I may be like, this is something that maybe should get added to the Stan language, and certainly maybe if that were to happen, this maybe should be a better named thing. Yes, you can see over here what obs actually is. You give it as input the observed mean. You already have the observed number of observations, and you have the observed variance. And we just pack those together into a vector, which first element is observed mean, second element is observed variance, third is the square roots of the observations, and then the last one is yet another transform of the number of observations. Just pre-computing these things. In theory, I could have just had it as 3 elements, and the last one being the number of observations, but pre-computing where you can is usually helpful in Stan. So 4-element vector as your observations. Down here, if you look, we've got just that observations vector as the left-hand side of the likelihood expression. And if you're interested, you could see what the actual form of getting this sufficient stats version of things. I understood it at one point, but I won't bother explaining it now. Up here is actually the central limit theorem. The observed mean is a function of the mean. The empirical mean is a function of the theoretical mean, as well as the square roots of the variance, divided by 3, which is the square roots of the number of observations. And then down here is the bit that talks about what the relationship between the empirical variance and the theoretical variance should be. So this is one where it can. So I normally deal with a lot of this Gaussian likelihood hierarchical data, and I've observed pretty substantial speedups from using this sufficient.
So just to clarify, this isn't going to work if we're in a regression context, right? Like we need a common mean to be able to use the sufficient statistics.
Not regression in the context that like if you had a number, so like the next example is that if you had again this example here where we've got a time of day and we're measuring, I don't know, people's heights, and I guess we'll deal with heights is a bad one. What would be actually no, it's not bad. One person's height through the time of day. You might expect a little bit taller in the morning after they've been laying down for quite a while, and then that's going to diminish as they go through the day as just gravity compresses their spine. But you know that you've got a ruler that is unreliable. Maybe you're trying to use some sort of, maybe that iPhone measuring thing, and you don't have a lot of confidence in it, so you take a bunch of measurements every time. And you lump those together. You don't try to say, okay, give like millisecond precision to the time of day. Say you just observe at a few times during the day, and you kind of lump during those time periods all those measurements together. Then you've got a bunch of observations that, for the purposes of the model, you're considering as IID, independent and identically distributed. But and that's a context in which you can compute a mean and a variance and the number of observations for that particular level of the covariance, the time of day observation. It turns out that you can actually mix. If you had like one time of day where you actually only measured once, that's fine. You can actually just add in that. You'd have to put it in as like a separate likelihood line, but in theory, it could be added in the, if n was 0, I could add that as logic in the sufficient code, but if you had a mixture of some with a bunch of IID observations and then some levels of the covariate that just had one, that doesn't foil anything. You don't need to do anything different. What it does do is it influences how you do model comparison using like leave one out, and in it doesn't make it impossible. You just have to do something different in the generated quantities block. No, I don't think we'll get to that today because I'm not very familiar with model comparison. I just know that that's a slight tweak on that. And if you're doing like prior predictive checks, posterior retrodictive checks, that basically to check that is the general model structure, giving you what you expect in terms of final inferences. It wouldn't catch things about like non-normality of your residuals by doing it this way. But there's a way to get to that, again, not in the model block, but in like generated quantities block. I like to kind of make things so that you get your model part as fast as possible so that you can fail fast. If that part fails, then you know something's wrong with the core structure. And then if you need to like look at more nuanced things like the normality of the residuals, like how appropriate is the normal assumption of this final likelihood, that would be something that I'm okay with leaving as a little bit of extra work in the generated quantities block. And the sufficient stats part for the multiple regression is just exactly the same. I think, actually, I didn't go through this one, but instead of having a single vector of, here it was a single observed mean, single observed variance, single observed count, and therefore our parameters were single reals. In the context of regression, well, we need to talk about like for every time of day that you're looking at, you need a observation, observed mean, observed variance, etc. So we're talking about a matrix of observations. Each column is a different thing, like mean, variance, n, or square root of n, and then another thing. But that's the only other change. So you have a row per level of time of day that you've measured. In the context of multiple regression, it's similar in terms of you have a row per time of day, you have a row per combination of your predictor variables. So if you only had two level variables, then and they're completely kind of crossed, then you'd have 4 rows in that predictor matrix, and so you'd have to expect 4 rows in this observation matrix. But otherwise, it's kind of very, it's the exact same as the initial structure. Here, I think I jumped to the location scale version of things. Did I have location scale in this original one? Yeah, I did. Okay. So this is a kind of location scale model with sufficient stats, and this one with multiple regression is also location scale with sufficient stats. Okay, so those are all so the core pieces are that we're gonna I have some code for Bernoulli hierarchical stuff, but we're gonna skip over that because it's very redundant. The idea of a Gaussian outcome. You can talk about regression on the where the central tendency of this thing is. You can also talk about regression on the amount of measurement noise. You can model things in terms of the individual outcomes as normal, but it's faster to jump to looking at the sufficient stats version of things. In these early things, sufficient stats versus not wouldn't have made like a obvious difference. I have found that it makes a decent difference in the context of the hierarchical models. So hierarchical. When we talk about, actually, I might pop over to my little window. Where'd it go? There we go. Do we have focus here? Actually, yeah, focus should be fine. I haven't ever figured out why it's so choppy. With hierarchical models, before we had these like fairly linear, like you had like in terms of what these plots look or these diagrams look like, there are kind of clear cut levels, but it's you have a distribution, parameter, distribution, outcome. With hierarchical models, there's just going to be more of those. There's certain kinds of hierarchical models that I realized that I have a specific definite or like idea of what hierarchical models are that doesn't encompass everything. Some people say hierarchical model is the definition of a hierarchical model is whenever you have one parameter whose value is or whose prior or value is dependent on the value of other parameters. And I've certainly seen that sort of thing. So let's see, what would be like, so in theory, a Gaussian process is itself usually a series of parameters that then have other kind of subparameters to them. And that would be technically a hierarchical model. We might have time to talk about Gaussian processes at the end. But I'm more talking about the scenario where you need some terminology. I like to talk about, individuals. And this is because I come from the world of psychology, and I'm usually observing a specific individual lots of times, and then I observe multiple individuals as well. So individuals, INDIV, groups, and then sometimes, like as I guess I'll put it up here, even though it's squishing now, I guess I'll put observations. And really, so observations are nested within individuals, and individuals are nested within groups. I guess I have this kind of backwards in terms of arrows, nesting, etc. But that's the nomenclature I use. People use very different nomenclature depending on the context. In fact, for the longest time, I misunderstood one of the Stan User Guides examples because they use very different nomenclature. You can have like in different contexts. So you have, say, individual schools as the unit of observation, and then school districts as the what I would call the individual level, and then you have states as like the group thing. Usually it's in the context of nested categorical variables. So if I felt that some set of measurements of each individual were perfectly able to capture the variability amongst individuals I'm interested in, then I would just have those variables as predictors in a regression that looked at accounted for the influence of those measured variables. But we can never measure everything, and to the degree that I know that there's a categorical identity to a given collection of observations, it makes sense to, in addition to any other predictors that are help identify characteristics of that individual, it also makes sense to give them a categorical label, which is usually like a participant number or school district, random zip code or whatever. So we're talking about, I think of hierarchical models as talking about nested categorical identifiers. And the nesting is important because like if we're talking about just a hierarchical model of the mean, a given individual will have their own mean, and their observations are going to be kind of clustered around that. And then the means across individuals will have, in a given group, if you had, say, multiple groups, the means for individuals that are in the same group will generally cluster together around the group mean. So you have this kind of cascading of distributions of parameter values. Usually, and yeah, I'm only really going to talk about a normally distributed, a normal model of how a given kind of level of the hierarchy varies according to the prior level. So we'll talk about individuals as having means that vary in a normally distributed manner from the group mean, and then observations within an individual as varying in a normally distributed manner from the individual's mean. But you can use any parameterization or any distribution of variability you want. It's just people tend to find the normal distribution fairly I guess, useful in this. So that I've only personally ever seen the normal distribution or an implied normal by using a log normal, that sort of thing. Any questions on just the general concept of hierarchy? I guess there's, like, once we've for a long time collected data that's hierarchical in structure, but we only had tools that were like were proven out in terms of the performance in non-hierarchical contexts, and they could only accept data. So like a t-test has no hierarchical structure to it. Even like a paired t-test, if you had individuals and multiple observations per individual, and you can do a paired t-test if those those observations have two kind of classes to them, so morning observations and nighttime observations. But if you had lots of observations in morning and lots of observations at nighttime for every individual, usually people would collapse those to a mean and then submit it to the t-test. And that's, one, throwing away a lot of data. You're throwing away both information as well as you're not reflecting the uncertainty about that information. But as you get to more complicated designs, it's not just that you're losing like your certainty. You actually start to bias your inference, particularly what we'll get to is in the context of correlations. If you do this process of collapsing things to a mean and then trying to talk about a correlation between two things, you're going to be biasing yourself to believing that there's no correlation when there actually could be substantial correlations. I have a question over here.
What are your thoughts on sort of group level estimate as a alternative to, like, say, try to do compute data? And is it computationally, what are your other advantages or familiar? And then I guess also conceptually, like, what are your...
Yeah, my experience with imputing data imputation, one is really only in context of experimental, where it's very tenable to have to make the missing completely at random assumption. So in that context, missing data is just an unobserved parameter that like the structures that I'll be showing you kind of just automatically handle. You don't need to do anything extra to impute data for a given person in a given kind of missing data condition. But the extra complexities that you have to add when data is not missing completely at random are things that I don't know a lot about. If I've come to a somewhat dogmatic or just strict view that like it's always better to, instead of try a simpler approximation, to do the effort to actually capture the full nuance and structure of data. So if that means having structures that account for that not at random missing data, rather than, okay, we're just going to ignore the fact that there's a whole extra level of observation here, I'd rather do that. I'd rather at least go down that path, particularly as it's clear that you can actually bias your inference. If it were simply the case that you're losing precision, but your actual like accuracy is the same, sure, yeah, just drop that extra thing for the simplicity. But because you actually can induce bias in important questions, I am, pretty strict on myself, at least when I'm modeling, to try to get to as raw a reflection of the data as possible. I'll get to the parts of that bias in a little bit. There's been good work in the psychology world talking about, we had... should I talk about that now? No, I'll talk about that in a little bit. I'll just tease you with the idea that you can bias things by not accounting for hierarchy. Okay, so back to actually how you express hierarchy in Stan. I'm trying to come up with a way of having like a generalized representation of hierarchy that will allow for arbitrary kind of n levels of hierarchy, as I've recently started dealing with data with that kind of level of complexity. But it's actually fairly rare, at least in the literatures that I've seen, to have more than a couple levels of hierarchy. You start to get, when you get like national level polling data, that sort of thing, you start to get a substantial like number of levels, 3 or 4, but at least with the data that I'm familiar with, usually it's only 2, and I thought for these purposes we'd deal with those first. So we're going to talk about the idea that you have individuals, and within individuals you have observations. We'll get into some regression where you've got, some experimental manipulations or observations within an individual that vary, or between groups of individuals that vary. But we'll start out with just talking about the simplest case where you've got a bunch of individuals and you're trying to measure each of them, but you're putting in some substantial measurement effort for each individual to characterize them. So you do multiple observations for that individual. So here, in terms of data input, it's a little bit different from the non-hierarchical. In addition to the number of observations, and here this is going to be determining the number of observations per individual. We also now have the number of individuals. And that, instead of being this is the binomial example. Oops. Because this here, observations, this really should be just a vector or a matrix of n observations and n ID. And instead of all of this, it would just be observations, and that would be a matrix of reals. So ignore this part and imagine that this word is matrix. So imagine you've got just this matrix where each row is an individual, I guess I have it structured so that each row is an observation and each column is an individual. And we've observed each individual an identical amount of times. We're going to generalize beyond that in a little bit, but for now, stick with the matrix equally measured people. So there's a couple ways when you encounter data like this, where you have multiple individuals each observed multiple times, you have to make some decisions about how to capture that hierarchy. One approach is to kind of ignore it. You're not ignoring it to the extent that you are like pre-processing the data, collapsing things down to a mean per individual, and then analyzing that data. You are looking at all of the data, but you are reflecting a model where you say the fact that I have these in separate columns as different individuals is completely arbitrary. Like, people don't genuinely differ from one to another. So that is what would be called a fully pooled model. Pooling meaning how much the data from a given person affects our inferences about parameters that are related to other people. So here we actually have the parameters of the model identical to what we had in the earlier non-hierarchical model. It's a single parameter mu, which is where the mean of the distribution is, and a single parameter sigma, which is the measurement noise. And so the likelihood is actually identical, except for now we've got a loop that's iterating over the columns of this matrix, but expressing that same normal model. So here on the left-hand side, we're indexing into each column of the matrix, but the thing on the right-hand side is all the same thing. It's all, everybody has the exact same distributed data. And another way that's, again, another like little optimization thing that you can do with this kind of data, but it wouldn't be worthwhile in terms of any noticeable speed up, is instead of passing in the data as a matrix, well, if we're saying all these columns don't matter, then we could just pass it in as a vector of that same number of elements, but just all packed into a vector. In which case, the thing on the left-hand side can just be the observed thing. And there are, even though you're doing the same number of kind of operations, there's some performance speed up of having no loop versus a loop, much less than in like R proper or Python proper. Loops aren't very expensive in Stan, but there's a slight improvement in kind of compute performance. But again, with these simple scenarios, not substantially. So that's the fully pooled. Usually not a good idea. If you have labels for people, then something about the people is differentiated. You've noticed enough different about the people to give them different labels. So that should suggest to you that you should use that information. So the alternate extreme, one extreme being people's identity doesn't matter. The alternate extreme is that people's identity matters ultimately, such that you can't expect any degree of similarity amongst people. So that would be the unpooled model. So the unpooled model has the same kind of data structure. Okay, I think here I keep it as a matrix. So that first version where we have to do a loop in the likelihood. But instead of, and here I'm only looking at the central tendency of the observations as the thing I'm interested in. Instead of a single value, a real here for what the mu is, now I have a vector of mu's, and I've called it ID mu. So a mu for each ID, for each individual. As a consequence, when we're looping over individuals, on the left-hand side, again, the column that's for that individual. And on the right-hand side, we now index into this new parameter, talking about the mean for that individual. If I expand to the full code, though, what we'll see is that this expression of the prior implies that there's no clear relationship among the people. It actually, I'm being a little bit too, I'm being inaccurate in that insofar as you're using the same prior for every single individual, there's kind of an implied loop here where ID mu1 is standard normal, ID mu2 is standard normal. if I were to kind of truly express something, I'd have like a different prior for every single individual. So they do share the same prior, but to the degree that the data informs what we should believe next, they don't inform each other. Data from one person doesn't provide any information about the what we should believe about the kind of parameter values for another person. So that's the sense in which they're unpooled. So that's the opposite extreme. That's also usually a bad idea. Sometimes you have to do it this way when you only have like a couple different people. Like if you only had 2 people, then really there's not going to be a lot of difference between this way and what I'll show you next. But certainly as you get more and more people and you start to have better kind of, I guess, information about how people might be distributed, how these parameters might be distributed amongst people. This next method is kind of the superior method, and if one was called unpooled and the other was called fully pooled, do we have any guesses what the middling and better position would be? Yeah, there you go. So partially pooling. I mean, you could have guessed like middlingly pooled, but yeah, partially pooling is the thing. I'm going to skip over the vectorized version. Actually, I shouldn't, because this introduces something pretty important that will come up. So again, we're going back to unpooled. So an individual mu for every person. If we didn't want to have to loop over these observations, but instead of a matrix of observations, just have a vector, we need some mechanism by which we identify which observation comes from which person. In this matrix version, columns identify which observations comes from which person. In this next version, we actually have, let me actually pull up, because we see that we've got this vector of observations. There's as many elements as back in the matrix representation, but now we've got them all just clumped into one vector. But now we also have another piece of data that identifies for each observation in that vector an int that tells us which person they are. So if you imagine, if people are familiar with the tidyverse in R, this is going from a wide representation, people as columns, to a long representation. And now we have a column that is kind of the indicator column. In the tidyverse syntax, it would be automatically named name. So we have an identifier for what column the new row came from. So that's it has to be. You might be tempted to call that a vector, but it actually needs to be an array of ints because we're going to use it as an index, and that becomes super useful with kind of more complicated hierarchical models. Is using arrays of indexes or arrays of ints to index into things. So the actual representation of the parameters is the same, a vector for the ID mu. And this time, we don't need to index on the left-hand side. It's just a big, long vector. But we are still indexing on the right-hand side. And it's by this thing that is the same length as the left-hand side. It's the same number of, it's this nobs times nid length. But it contains a bunch of ints that tells, that indexes into this ID mu thing and tells it how to expand this ID mu so that it's the same length as obs in the order that the observations, which person each observation comes from. This is the, I guess, non-sufficient version of things. When you go to the sufficient version of things, which I think I do in a little bit, you then are back to a scenario where you don't need to, the first way that you'd approach things is things are already collapsed to one kind of row in your observations per person. So, but that general idea of indexing into your parameters and having solves a lot of like ragged data and missing data issues. So here I'll actually just be going on with like fully vectorized. It also helps you account, well, I mentioned ragged data. So as I described things earlier, we had a matrix of observations where everybody had the same number of observations. Rarely in the real world, let alone experiments, do we have the ability to achieve such perfect measurement configurations, and often people have varying numbers of observations. That becomes a problem with the matrix version representation of the data, but is just automatically accounted for when you have it in the long format indexed version of things. Okay, so talked about unpooled. It's pretty silly. Fully pooled, usually not very worthwhile. Now we're going to talk about partial pooling. So the way partial pooling works, and the diagram over here is actually very useful. Here, I'll go to the unpooled, and we can see that we've got these two parameters. Sigma is just a single real, and ID mu is a vector. And there's a very simple, it's almost like it's, this technically might not even be considered hierarchical. You are kind of respecting the fact that these people come from different, but it's like they're coming from different experiments or different like data sets. They're not related in any way, and the model doesn't encode any relation amongst them. The partially pooled, it has like an obvious extra level of complexity, extra level of hierarchy in this diagram here. We'll start from the bottom. Observations are normally distributed, and that's the same as before. These normally distributed observations come from a real that's sigma and a vector that's the ID mu, that's the same as before. The prior on the sigma is the same as before. Now we've got, instead of a standard normal on this ID, we actually have a normal. And this normal, in turn, has other parameters associated with it. So the idea here is that in addition to doing inference on what a given individual's mean is, we're also trying to ask what the mean of all of the individuals are, and what are the variability of all of the individuals. So what is the variability of the individual means, and what is the mean of the individual means? Any unclarity in that? To do that, we actually are kind of reverting to almost what we had in the original non-hierarchical case, in that if you kind of, I almost did it on my screen to cover, but so if you imagine just the ID mu is now the data, now we've got a model that's exactly like what we had at the original non-hierarchical. We've got some set of outcomes, and we're modeling it as a normal distribution, and there's some mean for that normal distribution, and there's some variability for that distribution. So we have a real that reflects the mean, we've got a real that's lower bound that reflects the standard deviation, and we put some priors on those. And the extra complexity is that we then use, we then express that this kind of next variable, the ID mu, which I guess here, I'll go to the full code so that I can refer back just in here. This vector of ID mu's has a normal distribution that has a mean that's this thing, and a standard deviation that's this thing. Then once we get that, we then use the standard vectorized, indexed expression of the likelihood, so it's that each observation is associated with an ID, so what element of this vector it's associated with, and then everybody has this common sigma. Does that kind of make sense as like so the reason why this is called partially pooled is that the data from people actually do start to influence the estimates that you get from other people. through their common connection to this these two variables. So if you had, and this typically is related to the amount of data you have per person and slightly to the amount of noise in each data, but here we have a model where everybody's considered as noisy as everybody else. So if you had one person that had 2 observations, and everybody else, or I guess, let me just flip it around. Most people had just 2 observations, and you had one person with 1,000 observations. You're going to be very confident that that person with 1,000, their mean that you've gotten is an accurate representation of that person's kind of true mean. Now, real world, as you get actually larger amounts of data, you tend to be collecting data under different measurement conditions. Like, it's hard to get 1,000 things in a very controlled situation, so there's that extra complexity. But let's imagine a synthetic world where we can actually control all possible factors in the measurement environment, and we genuinely have this situation where we have lots of data for this one person and very minimal data for everybody else. Having that person in the data set versus not is going to have a pretty big influence both on the mean on these these parameter values as well as each individual's parameter values, because everybody in a partially pooled model, people tend to the degree that we are uncertain about where their individual mean is, they actually tend to get pulled towards whatever the group mean is, and that person is going to be inordinately influential on what the group mean is. This sounds like a bad thing in the context of that extreme scenario with one person lots of data and everybody else very little data. That arguably would be a bad thing. But in most cases, it's actually a very good thing, because if you have a few people with actually very little data, the phrase is they borrow power from the people with more data. And you get, one of the consequences is that you actually get more accuracy in both precision and accuracy in estimating what a given individual's parameter is by the fact of having other people with cleaner and more data. The cleaner part is just about how variability, how much noise is. Again, in this model, we're just modeling things as everybody has a common amount of noise, so that's not as pertinent. But if you have somebody with just a few observations, again, central limit theorem is that those couple observations, you're not going to have a very precise measure of what their actual mean is. Whereas for those people that have lots of observations, you're going to have a much more precise and accurate, I think, estimate of where their mean is. So to the degree that we're modeling things as everybody coming from the same common mean, and we're getting good estimates of what the variability should be, extreme outliers tend to get pulled back into closer to the group. So it's useful in terms of where you'd normally, from kind of point estimate frequentist methods, have to deal with extreme outliers. They get automatically kind of pulled in towards the group and look a little bit more, they act less troublesomely in these Bayesian hierarchical models. Questions? Yeah.
So I'm clear on terminology. Is this sometimes referred to as shrinkage?
Yeah. Are there other contexts in which? No, that is the primary context in which that phrase is used. Is that you have usually, I think it's a little bit more generic whenever you have multiple parameters that all kind of have a kind of common root. But certainly in this context, you get better by having them influence each other. They shrink in terms of their uncertainty about any given individual, but then they also all get pulled in towards the mean a little bit, proportional to how much data they have, how noisy that data is. If you have a noise varying accommodating model, and also how extreme they are. So the more extreme people get pulled in more dramatically. So I would love if this were the story of, in terms of how as practitioners we need to think about hierarchy and the kind of conceptual transition from non-hierarchical to hierarchical. There's a slight annoyance when it comes to Bayesian sampling of hierarchical models that some people have proposed some solutions to, and I think there's the sufficient stats thing actually has some pointers to even in Stan a solution to, but it's definitely not implemented yet, which is that if I had, as I've expressed here again, you've got this ID mu, its prior is no longer just like a standard normal. It actually has arguments, there we go. Arguments of its prior are other parameters. As expressed this way, sometimes you will get good sampling of your model, and sometimes you will get really difficult, long chain, very, long compute time and high divergences sampling. And it's pretty predictable when those cases are going to be. That's why I think that there's some path to actually making this transparent to the user, and you guys won't have to worry about it. But for right now, you actually do. So this problem is where you'll see the terms centered and non-centered as terms used, because there's different ways of expressing kind of the math that implies this distribution, a normal distribution on mu with a mean of mu mean and a standard deviation of mu SD. If you, let's see, I guess, yeah, so do I just go there? Okay, yeah, I will. The phrases centered and non-centered are actually not the way it's actually described in the user manual, and the centered and non-centered to actually only deal with part of what the issue is. I've transitioned to calling it centered and scaled, and uncentered and unscaled. So the way this is expressing a centered and scaled model. That is, that the prior for this thing that is a parameter in our model has as arguments in its prior other parameters in the model. That's what the centered version is. And I'd love to be able to just have it, that's how we express things all the time. The alternate way of expressing that is, and let me go to the diagram here. You have this ID mu thing here, it's got its normal distribution and its parameters up here. The alternate, the uncentered and unscaled, has a slightly different structure. ID mu here is now a product of three things. The mu mean, the mu SD, but then instead of having those two kind of converge on a normal distribution, i.e. defining its arguments, they're actually just pointing directly to this ID mu, and then furthermore we've got this other thing, ID mu underscore. I put the underscore, that's just my own convention of reminding myself that, hey, this is a parameter that needs to be transformed before becoming what it's ultimately going to be used as. So in the earlier model, we had as a parameter a vector of NID long, that's ID mu with no underscore. Now we've got ID mu with an underscore. And its prior is going to be a standard normal. So mean of 0, standard deviation of 1. And we actually compute ID mu as a derived quantity. Usually people would put this in the transform parameters section. I've somewhat, there's there's some uses of the TP section. I've started just putting most things in the model section. I can talk about that at another time. So the idea here is that whenever you take something that's normally distributed, you can always transform between a normally distributed thing and a that has a mean and a standard deviation, and a non-normal, or sorry, a standard normal distributed thing. To get from the normally distributed one to the non-normal, you just subtract the mean and then divide by the standard deviation. And then to go back the other way, you multiply by the standard deviation and add the mean. The order does matter. You have to go one way, you have to multiply the standard deviation first and then add the mean. So that's how we go from this standard normal to a non-standard normal. So that has the mean of the mu mean and the standard deviation of the mu SD. We take that standard normal thing, we multiply, and I multiply. That's, even though this is just a real, I have just gotten to automatically do that. We multiply by the standard deviation and we add in the mean. Mathematically, if you had the same parameter values for, I guess, the mu and same random number generator seed and things, you get out the same values for what ID mu is in both cases. But what the relationship amongst variables that the sampler sees as it tries to kind of explore the space is different. And it's, in some cases, it can explore one space easier than the other. The general description is that when you have more information dense data, so lots of observations per person and very clean observations, so low measurement noise, centered parameterization is going to do better, so that natural kind of one. But when you're in arguably the more common scenario of having less data and noisier data, the non-centered is going to perform better. You can actually just code the data in both ways, and I'll show you actually a quick way of doing that in a moment, and just try them out, and you'll see just a noticeable sampling time difference, even in like the initial warm-up periods, to determine which one's going to be better. And for a long time, we just would tell people, okay, try uncentered first, and then switch over to centered if uncentered doesn't work. Because usually people are starting off with low data quality and trying to make inferences from that. Much more rarely do people kind of have enormous amounts of data and have the really need the centered data. In fact, BRMS behind the scenes by default uses an uncentered, and the last time I talked to Paul, there just wasn't any facility to switch over to centered. I should show him the trick that I have to make that fairly trivial. But you can code it the two different ways and run it and see which one kind of converges faster. If one of them converges fine and the other one doesn't, just you go with the inferences from the one that converged fine. A couple points. So I switched back to talking about just uncentered and centered. It is important to account for the fact that it's actually centered and scaled, because centering is about where the mean is, and scaling is about what the standard deviation of the prior is. So you're doing both here. I've been meaning to look into under what conditions are those dissociable? It's just, I guess, amongst the Stan folks in the room. Has anybody explored that at all? Like, I feel like certainly the scaling is actually maybe the important thing, and I almost wonder if the common nomenclature about talking about centering is actually somewhat orthogonal, because certainly since the noisiness of the data implies that the scale matters. Anyway, okay. Something I've been meaning to explore. Certainly.
Would it matter for things that have a mean really far away from zero, since values get initialized between -2 and 2?
Well, that would be more related. That wouldn't necessarily be solved by centering versus non-centering, because I've definitely seen the centered versus non-centered difference from synthetic data that's being generated with means of zero. So I don't think that that's indicative that centering is important. The other thing that's somewhat not talked about as much, though I learned about it it has been talked about. Mike Baconcourt has a great, though dense, hierarchical modeling, blog post that talks about this, which is we've actually gone through and we've treated every single individual identically, such that we've assumed that they all need to be centered or they all need to be uncentered. I described to you a scenario, well, as I described earlier, like people can vary from one another in terms of like the amount of data that they collect and how much noise, particularly in my world with psychology, there's great variability in how kind of noisy people's behavior is. Usually our measurement instruments aren't going to like really change their noise characteristics from one kind of measurement thing we're measuring versus another, but if we're measuring behavior, that tends to manifest its own noise that can vary dramatically. So certainly I think there's good prior expectation that maybe if you had enough data on everybody, it's not going to, like people are going to similarly require centered versus not, but in, again, lower data scenarios, those differences amongst people are going to amplify, and some people might actually need centered and some people might need uncentered. So far, that hasn't been enough of a problem that people are complaining about the default everybody either non-centered, default everybody non-centered in BRMS, for example. But I wanted to mention it that you can, another kind of, in the same sense as I suggest, adding the uncentered and unscaled as the name of what we're doing here, you actually would refer to what we've talked about so far as monolithically uncentered and unscaled, i.e. everybody is being treated the same. I showed you this one way of doing the uncentering. There's another way of doing it, but it got added not recently, but like substantially after people realized that a lot of the time we want to do uncentered and unscaled, which allows you to go back to using this expression of things rather than adding all this extra code to do this extra computation. And that's in what's called the offset and multiplier in the declaration of IDMU. So up here in this original IDMU declaration, it was declared just with a size. And down here in this other IDMU, it's got declared with a size. Ditto, this one's declared with a size. With all parameters, you can express things. I think we've seen like the standard deviations as having something in between these greater than, less thans as some sort of argument. So, you know, how did because this is supposed to go to 330, right? Sorry? Oh, okay, yeah.
I had the problem this morning too. It just like did that, and
Okay.
then after 30 seconds, you could make it come back.
Okay, but I actually wasn't here when they started it, so, you may restart. Okay, so presumably it's touching something on here. All right, I'll figure that out in approximately 25 seconds. There we go. It's the same source on both projectors. Desk HDMI. Yay. Okay, great. So we've already seen one argument to the specification of the declaration of a variable, which is whether it's bounded or not. There's actually an upper bound you can put on things. We saw that at the very beginning with the probability parameter that was bound at lower equals 0, upper equals 1. In addition to these lower and upper bounds, you can have what's called an offset and a multiplier. Offset acts like that centering, that adding or subtracting a mean, and the multiplier is the same as multiplying or dividing by the standard deviation. And I'll show you what that looks like down here. So you have to express things here in the order. Let's actually, I'm going to pull up the full code here. So, so I'm telling it that the offset for this ID mu is mu mean, and the multiplier for ID mu is mu SD. What that does behind the scene is it, Stan is trying to sample from, like it takes what the unconstrained space sample for ID, each element of ID mu is, and it automatically adds in whatever this mean is and multiplies by whatever this standard deviation is. So it's automatically doing what we had done by hand in code here. The one important note is that it actually, like, I can't declare ID mu above the things that are parameters that determine its offset and multiplier. I have to have those declared first. Just an order of operations type thing. It needs to know what mu mean is before we tell it to use that as an offset. But that does then enable us to express things as this monolithically, express it in what you would be more familiar with and what would come more intuitively as the way to express the priors and the structure of this model. And then, so that's one neat thing. So we then need to just modify this bit to go from the centered to non-centered. We don't have to have this extra parameter that then fills up our CSV files and adds more data storage, but we still would need to switch between these two, have two different Stan files, and that's annoying. So another trick to just have it so that at the time that you submit data to sample, you can add a data variable that's a 1 or a 0, and 0 means uncentered, unscaled, and 1 means centered and scaled. You add in a data variable that's an int. It's either 1 or 0. And then you use the conditional operator in expressing what the offset is and what the multiplier is. So in the case that this data variable comes in as 0, then this Stan interprets zeros as false, and do I have this backwards? Centered and scaled being 1 will lead to this. Yes, I have it backwards. So this logic is backwards. So this variable should be called uncentered and unscaled, in which case, if you want it uncentered and unscaled, oh no, I had it right the first time. Yeah. So yeah, if you want it centered and scaled, then you want the behavior of this kind of expression of the prior to be the same as that original thing where you didn't have an offset or multiplier. So you want an offset of 0 and a multiplier of 1. When you want it to be uncentered and unscaled, then you want the offset to be mu mean and the mu SD to be, or the multiplier to be mu SD. So that's a quick, easy way to do it. It's still annoying to have this kind of user-dependent, try one way, try the other way. It also starts to get more cumbersome if you need to go to non-monolithic.
You want to take a break?
Oh, yeah, actually, it'll be a good time for a break in a moment. I'll finish talking about this one. So it can be annoying to talk about if you need to go to non-monolithic, that starts to be hard to then implement with this kind of logic. As you have more variables that are going to be kind of hierarchically structured, then you have to kind of iterate between. I have some hope that we can figure out some general rules relating the number of observations and the noise in those observations relative to the scale of other aspects of the model that can automatically toggle things to one or the other. There was actually a paper a while ago, Maria, I always forget her last name, but that had like an automatic reparameterization person by person that would, during the warm-up, figure out whether they need to be centered or scaled. And that's in PyMC3, but not Stan. She had to actually create a special language for Stan that had a different warm-up to do that. And I guess it just hasn't been popular enough to come to Stan. Most people are pretty happy with uncentered as a fairly common default. There is a way, if you wanted to do the non-monolithic, so separate thing for each person, there's a way to do that. I actually won't go into the code that much. You just enter for every single person a 0 or a 1, and there's some code here that will go through and specifically create 2 variables down here in the parameters, one for the people that need to be centered and one for the people that need to be uncentered. And then you combine those with their indexes as appropriate. This will be a good kind of point to break, and then we'll start talking about like more interesting structures. So this so far has been like the barest hierarchical structure, and we'll start talking about some cooler stuff. Quick break. How much time should we take for a break?
Yeah. Perfect.
Or sorry.
Whatever. I think we still have 2.5 hours. Or 1.5 hours.
Okay, so this is the halfway point. Okay.
Yeah.
Cool.
That's good.
Okay. So from now on, I'm actually going to stick with the non-centered and monolithically non-centered. So the last time we saw something non-centered all by itself, it had this structure here where you've got sigma is just going to be a single real, assuming everybody has the exact same noise measurement, noise variability. And everybody's going to be slightly differing in where their mean is, and we're actually going to have an explicit model for the distribution of individuals' mean as itself having a mean and a standard deviation. Okay. I just realized I wrote some models that I didn't include here, but I can add them easily. So the next little nuance I want to show is this is you see this a lot where, again, people ignore the noise variability. They kind of just call it one thing, everybody's got the same, or sometimes you get people, you get things where each individual gets their own noise variability, but they leave that as like an unpooled, unpooled thing, so you don't get any partial pooling advantages. I'm very into the location scale modeling stuff generally. I've found, at least in my domain, human behavior tends to be fairly noise prevalent, and the noise is meaningful. It has information content in it. So that's why I'm very into location scale. So how would we turn this into a location scale style model, but still respecting that there's a hierarchy here? Hopefully, the way I've kind of introduced some of these things from the very simple non-hierarchical stuff, we're starting to get a concept of like there's kind of plug-and-play structures or pieces that you can look back at earlier models and see, oh, if I just want to make this part of my model be more, have like this extra structure, I can actually just grab the code from that or other and generalize it. So this is the first, I think the first case where we'll see that in the context of the hierarchical models. So again, this is the one where sigma is just this real, here if I go to the full code, sigma is just a real constant across people, and we want to get past that. We want to actually model it just like this mu is being modeled, so that there's variability amongst people and what their measurement noise is, and that variability has structure to it. So I'm going to scroll back past all their centering, non-centering stuff. Actually, a question came up during the break that I should probably address, which is that it's there could be confusion since we're using similar terms, centering and scaling. At the very outset, I talked about when your predictors are coming in, it's usually a good idea to center and scale them for the purposes of how the model kind of initializes itself. And when you do that kind of centering and scaling of your predictors, you generally will then need to adjust your priors so that they kind of maintain the meaning that you intended for them, and prior predictive checks are the way to do that, which you'll see more tomorrow of how to actually do prior predictive checks in Mitzi's talk. But that's for, again, the predictors, the non-categorical things, the like if you're talking about time of day or somebody's, the influence of somebody's, I don't know, IQ on their income or whatever. So those are the continuous things that each thing has, you're trying to eventually do inference on the influence of that measured thing on some other measured thing. That's a separate centering and scaling issue or procedure than the centering and scaling that we just talked about a whole bunch in the context of hierarchical models, centering and scaling. The one about predictors, you generally handle with outside of Stan. Before you give it data, you center and scale, and then you make sure that your priors are the right structure to get out to actually be what you want them to be. But this centering and scaling of the hierarchical structure is something you just have to run both models, really. Start with the uncentered, transition to the centered. Hopefully down the line we'll have a few more automated tools to actually do that for you in Stan itself. But right now, the common thing is start with uncentered. If it samples badly, move to monolithically centered. If that samples badly, you might need to then go through and look at your individuals and try to center some and not others. So that's clarification from the break question. The next thing is talking about how to, there we go, do a hierarchical location scale. So another reason I like nice symmetric diagrams, and so having this asymmetric diagram up here is irksome to me, so I like to have this nice symmetric one. So now this, we've got the mu, well, it's switched sides, but mu is the same as before. It's got this hierarchical structure, and this is the non-centered version. So we've got, if I go to the full code, mu is the exact same thing as before, where we have a kind of helper variable with the underscore at the end. That's going to be standard normal, and then a helper parameter. And then there's another derived quantity that is actually the thing that we're interested in, which is just an arithmetic derivation of that helper variable plus the mean in the SD that we're trying to capture as, I could have actually put this in here as like that toggled normal version. Because I started with Stan way before any of those tools became available, I just automatically write non-centered in this structure. I probably should switch over. So that mu is being treated the exact same, but now we've gone back, and if you recall when we had the non-hierarchical, when we wanted to do location scale, we moved away from talking about the standard deviation of the likelihood distribution of observations and started talking about the log variance, which I talked about as a parameter called eta. And eta now just gets treated exactly the same as the mean, or as mu. So it gets a mean, it gets a standard deviation, and it gets this helper variable with the underscore. And then when we're doing these derived quantity computations, which again could go in the transform parameters, but I just always put them in the model block, it's an arithmetic derivation of the combination of the actual parameters. And then if we're using this normal likelihood, you need to transform from log variance to then standard deviation. The normal, the sufficient, which I haven't, when I was putting this together, I put it in kind of out of order. If I were to go back and do this, I'd actually make the sufficient what I'd show now, because there's an exception that we'll get to at the very end where you actually can't use the sufficient for some kinds of hierarchical models. But for most that I've used, you can. So in that sufficient representation, it expects the variance as the kind of parameter, the scale of the parameter that you're doing inference on, so you don't need the square root part. But otherwise, you'd use the exact same structure. So pretty simple kind of plug and play to suddenly translate from a very conventional location is the only thing we're interested in to suddenly having the ability to speak to variability in the amount of measurement noise and capture the information that's in that, I guess, that data, the data that is the error variability. Another reason why I like the location scale models is, again, in my domain. It's not only that the error variability has structure to it, its structure is related to the structure in the means. So I deal a lot with like simple video games where people are responding very quickly, and we usually just automatically log transform that data so it looks a little bit more normal. But on that scale, then the mean of a given person's kind of observations in a given condition of the experiment typically scales pretty linearly with the variability of their distribution. So they can mutually inform. And the way this one is structured, this hierarchical location scale that's on the board here, they're actually not mutually informing at all. There's like no connections between these two kind of branches of this tree here. So that reflects the fact that they're not mutually informing. So I want to get rid of that part. I want to add some ability to have them inform one another, capture more information from my data. And to do that, we need to actually build up a little bit. I could do it fairly trivially like this, but it won't be as generalizable. So the first thing we're going to do is look at a more compact kind of just version of representing all these variables. It can be useful as you get like a lot of parameters to then start thinking about what you're doing in common to the parameters. And then if you're doing a common thing to a bunch of different parameters, just pack them in some, like here I've got these two vectors, but I'm doing this kind of same thing to them. So probably might make sense, instead of having two vectors, just have a matrix with two columns and then just one variable. And that just makes your code a little bit more compact, but it also ensures that you don't do like minor typing errors and things like that. So we're going to switch over to this more compact version where instead of a separate vector for mu and a separate ID mu and a separate vector for ID eta, we've got a matrix with two columns. And I've named it so that mu and eta, ID mu eta. So we've got this one thing. Similarly, we had a vector up here for a real for a mean for mu and a real for a mean for eta. Now instead we have, instead of two reals, we have a vector. In fact, it's a row vector. Similarly, we had a real for SD of the mu's and a real for an SD of the etas. Now we've got a row vector of length 2 for the SDs. So it's just packing those variables together because we know we're going to do the same kind of thing with both of them. It's a little bit arbitrary in this case why we would do that, but as we get more complex structures in a moment, it'll be a bit more obvious why we would do it that way. But otherwise, well, it does make it so that we can have a single expression for the means prior and a single expression for the SDs prior instead of having the two separate lines. Not going to be a noticeable difference in code execution. We have the ability to turn, instead of two calls to standard normal to express the helper variables, individual vectors, priors. We now can take this matrix. Matrix can't be on the left-hand side of the kind of well, there's a few structures like correlations and things like that that it can be on the left-hand side, but for the standard normal, you can only have a real or a vector or a row vector on the left-hand side. So we have to turn it to a vector. But this kind of expression is kind of a temporary turning it into a vector. It doesn't stay a vector. And then we're doing this, again, we're computing the same kind of derived quantity for each, from the ID mu and ID eta. So we take the thing, we're doing some sort of scaling by multiplying by the standard deviation, and we are adding in the means. The reason why, so there's a couple kind of new things. So this isn't as plug and play as the previous example. So the new things I already mentioned, we're using a row vector instead of a vector. The row vector is, I actually didn't understand it at first, but I quite like it now, that there's, when you want to talk about something that really in memory, actually, Brian, do you know, is a row vector genuinely stored differently in memory than a vector?
No, the 1D objects are the same.
Yeah, okay, that's what I thought. When you, it does imply a difference as you start like using them. So if I have this thing rep matrix and I give it a row vector, and so the first argument is, so rep matrix takes in either a vector or a row vector and turns it into a matrix. And the first thing is the thing that you want to turn into a matrix by repeating it. And then the second argument is how many times to repeat it. So how big you want it to repeat. So if it's a row vector, it makes a matrix where each row is identical to the other rows. If it's a vector, it will make it so that each column is identical to the other columns. So because we have this mu eta where people, individual, are the different rows, and we want everybody's rows to be, and we've got the means, so we want this column to have one mean and this other column to have another mean. We have to have the means as a row vector, in which case, I guess if I'm talking about the means, adding that to whatever this product is, it is equivalent to saying adding like the same number to all of these rows and then this other number to all of these rows. And then ditto when we're talking about multiplying to scale to get the standard deviations of the columns right, we are using the rep matrix there, and it makes sure that we're multiplying all of the rows in the first column by the first element in this standard deviations row vector, and then all of the elements in the second column of this matrix by the second element of the row vector variable SDs. So yeah, this just gets out the exact same computational result of doing it separately for the mu's and the etas. It's just faster, like to type it out, and I find it more I find it useful conceptually because it kind of unifies a bunch of things instead of having lots of lines. And then the consequence of that, though, is that once we get to the part where we are using that thing, instead of having just two vectors that can refer to separately, I need to index into it. So with the indexing, I guess, syntax that Stan uses, I can omit the first. So I don't know if they covered this in the intro one, but when you're referencing a matrix, the first element of the indexing is the row, and the second element is the column. If you omit one or the other, it selects all of them. So by omitting the rows, but including an index for the columns, it's going to select all of the rows and then the indicated columns. So this selects the first column of that matrix, and then this one selects the second column of that matrix. So I kind of packed everything together, and then finally, when I need to use them separately, I then use indexing to pull them back apart. But otherwise, the kind of expression of this as a normal likelihood is the exact same as before. Once we get those columns, we still have to index by what person is associated with which observation that's on the left-hand side of the likelihood expression here. Is that like pretty straightforward in terms of yeah, I find it simplifies things. It also, for this, I guess, this trivial example where we have these two things that we want to treat the same, and if I want to additionally add this extra kind of relationship among them, I can establish that relationship in a couple of ways, but the kind of canonical way is to express it in terms of a correlation between these two columns. So right now, even after I've transformed everything to the actual value that reflects each individual's mean and each individual's standard deviation, these two columns, there's nothing in the model that expresses that we are interested in a potential correlation amongst these things. The data might have a correlation, and the end result of doing inference might have estimates for these, like if you pull out the posterior for each individual, there might, and then you did like an empirical correlation sample by sample, there might end up being a correlation there if the data suggests a correlation, but there's nothing in the model that's explicitly allowing proper inference on that correlation. And in fact, that like estimate from the posterior isn't really a proper estimate of the kind of theoretical correlation. So it's better to always, if you are interested in something, try to include it in the actual structure of the model than trying to kind of compute it out as a kind of a derived property. So that is what this second, or I guess this last model in this thing, but I've got a bunch more here, achieves. So back up here, we had 1, 2, 3 things that influence the derivation of this ID mu eta, and now we're going to have 1, 2, 3, 4 things. So the fourth thing being Cholfac core. I won't go into the math because I don't understand the math, but the general idea is that they're, I guess I could have just shown you the version of this where it's a correlation matrix. Whenever you have, well, I guess if you have two things, you have a 2 by 2 correlation matrix. On the diagonal is a 1, and then the upper corner and lower corner are going to be the same number, which is the correlation between those two columns, or those two variables. It turns out that like the math to then sample to express like a correlation is more efficient, and I might be wrong about this, but I actually think that it's also associated with the when you're trying to do non-centered. See, this is another thing that I haven't seen explored yet, is doing centered but still using the Cholesky factor correlation expression of the correlations. But usually when people are doing non-centered generally, they also do this representation of how to encode the correlation between things. So you'll see this most often. In the Stan user guide, they'll show the other way of doing it, and then immediately say, but it samples better if you do it this way. So I thought I'd show you the way that is kind of the final recommended way of doing things. So you've got this variable. It actually has this weird type to it. It does reflect a 2 by 2 thing, but since it's like symmetric about the diagonal, the actual implementation just shows the size of the non-diagonal, or I guess the size of the elements that determine the height and width, and it's a square matrix, so it's always just a single number. And Stan behind the scenes will figure out how to, like, what this is, and how to sample from it. It has its own kind of unique class of priors that you can use. Usually people suggest the LKJ prior, and there's an LKJ core if you are expressing it as a correlation matrix. But if you're expressing it as a Cholesky factor of a correlation matrix, you have to use the LKJ core Cholesky. the argument, there's a single argument to that prior, and that kind of determines how concentrated to, I guess, how strong you want to, what would be a good way of expressing this? Higher numbers express higher credibility to independence. So if you had, like, I actually have seen, like, as a default, some people put, like, 3, I guess this isn't an editor, so some people put 3 as a default. 1 is truly flat. So I have no prior expression of, like, or that I don't have any, like, expectation of independence. That's what I tend to default to, because if I'm adding in this correlation, I don't want to be too skeptical of correlations. Like, I put it in there for a reason. I haven't seen much justification for why people will default to higher numbers. That seems to be somewhat self-defeating to add in the capacity for correlation, but then biasing the model to see things as independent. But there might be, certainly this is a realm where there's a lot of nuance, as I'll describe in a moment, or in a couple examples from now, that I could be wrong about that. So and then once you've kind of added this parameter and a prior on that parameter, you then need to use it somehow. Happily, it's actually a very easy thing to use in that you, previously we didn't have this line in the expression here. We had simply this standard normal matrix full of standard normal random values, and then we multiplied it by this matrix that reflects the standard deviations repeated for every row, and then the means repeated for every row, and added the means for every row. But now we've added in this just multiplication. And note that here I'm doing a ELT multiply, the dot asterisk multiply, which is an element-wise multiply. But here I'm doing a proper matrix multiplication. And Stan behind the scenes knows how to take this and know that it actually is a matrix and how to multiply these two things. So again, I won't go into the math of how that actually transforms things to the proper kind of matrix representation. I didn't add that to this. One slightly annoying thing is that you then would ask yourself, what is the, well, actually, I think with a 2 by 2, well, with a length 2 Cholesky factor core, the numbers that come out is actually just straight up correlation. As you have more things that you're correlating, you actually have to do something to it to get out what the implied correlations are, what the implied correlation matrix is. But I've got some code that I'll show you that does that easily. But yeah, it's,
Quick question.
yeah,
to anything. Like,
yeah.
If you,
Oh, sorry, I'm having trouble hearing.
so if you don't have that line, which is Cholesky factor is occasionally correlation, would it, are you like, is there a difference between putting an implicit uniform prior with the Cholesky factor of the correlation matrix versus putting a uniform prior over the correlation matrix? Say, instead of doing Cholesky factor, just correlation matrix.
This is a realm where so the question was, if we had the correlation matrix parameterization rather than a Cholesky factor correlation parameterization, does it, if you had a uniform prior on the correlation matrix versus a LKJ core Cholesky, or LKJ core of the, well, you can't, I guess if you omitted the prior on the correlation matrix, I think the sampler would complain more often that there's a, I'm not, my gut is that there's no difference, but I might be wrong. don't feel like there's a difference between those. What is the, oh yeah, the term I was blanking on was if you omit a prior entirely, it might make it more likely that the sampler goes to areas of the potential configurations of the matrix that are not positive definite. But I actually think that even in the expression that something is a correlation matrix versus, like if I just put a matrix here, so a 2x2 matrix, and then no prior on it, that is definitely going to yield lots of errors. It could get passed and eventually sample appropriately, but it is more likely to hit errors that it will say that this correlation matrix is not positive definite. Actually, the way this is structured, there's nothing that's going to check for positive definiteness even here. So it would probably fail other ways in a diagnostics if I had no prior on just a regular matrix. But now that I think about it, I'm pretty sure even the correlation matrix data type, if you declare it as a correlation matrix, it will do a check for positive definiteness on the proposals, or it does something from the unconstrained space to the constrained representation that ensures positive definiteness. So I'm more confident in my gut reaction that it doesn't matter whether you if you're genuinely have no prior on the correlation matrix, it doesn't matter if you have, as long as you've declared it as a correlation matrix or a Cholesky factor correlation object or, I guess, variable type. It shouldn't matter whether you've added that prior or not. I now do because I like to have that dot in my diagram. And it, pardon me?
It's just done with just add the Jacobian for the translation.
Sorry, I still couldn't hear you there.
It's just done with just add the Jacobian for the translation.
See, I feel like that's part of the translation from the unconstrained to constrained, that it automatically makes sure that it's the automatic constraint, automatic, when you express something as a correlation matrix or a Cholesky factor of the correlation matrix, the thing that it adds as a Jacobian to go from the unconstrained to constrained is the thing that ensures that gets to a flat positive definite thing. And so adding in a correlation, a prior expression that also implies flat is probably redundant. But I like to do it now because it's, I've never noticed it actually making a big difference. Generally don't deal with correlation matrices that are super big and large. And certainly I'm also confident that it doesn't matter, if you have a flat correlation, you can express that either as a correlation matrix with an LKJ core of 1, or as a Cholesky factor of the correlation matrix with an LKJ core Cholesky of 1, and those yield equivalent expressions of flat prior. Okay, so we've got this thing where we now have the ability to capture, I've introduced the location hierarchy and how to express a hierarchical model of the location of the Gaussian outcome. We've then added in this idea that we might as well do the same thing to this other parameter of the Gaussian, which is the variability. And furthermore, we can have them mutually informing one another. This is the last on that. Do I want to? Yes. So I've got some other models over here that I guess I just didn't add to my document yet. Let's see. Hierarchical Gaussian regression. That's the location scale, compact, and that's with the correlation. So yeah, the first one I want to show is so far these hierarchical models with location and location scale have all still been very trivial in that there's no real like interesting inferential questions where it's just you're measuring one thing about people and you're getting some inference on an individual person's mean and variability and what the group level kind of mean and variability is, but you're not looking at like the influence of a variable or anything like that. We're usually much more interested in like the influence of our experimental manipulations or some sort of observed covariate. So there's a variety of ways that those can kind of manifest, and maybe I will switch over to this. So we can have, again, let me, do I have? Yeah, all right. We can have, and let me actually do this, that's the top down, kind of like in the diagram. So we have the observations here. Observations here, and above that we've got the individuals. And again, terminology is mine because I usually come from observations, individuals, groups, but other people will use different terms, and you just need to kind of figure out from the context what a group means and what an individual means. But the next thing is fairly generalizable except for the words, which is that you can certainly have a scenario where you've got groups characterized by experiencing different levels of some predictor. So I like to call that, what actually did I use it in this? I think I called it between groups. So in the between groups, a given group experiences only one level of whatever thing you're measuring. So they're either all in one state, like if state was no, state wouldn't be, because that's more of a categorical. They're all, if you binned SES or, like sex. Like if you had some sort of animal model and you had experimentation on the influence of a drug and you were doing proper research and making sure that you're looking for sex differences instead of being like traditional research, only looking at the male mice, which was silly. You would have this categorical thing, which is sex, and you can look at the influence of sex. Not an experimentally manipulated variable, but it's observed. That's fairly clean. Any given individual in that group is only only reflecting one level of the thing you're interested in, sex. The other kind of manipulation is the within individual. So this would be the type of thing where for a given individual in a given group, that individual experiences multiple levels of the predictor that you're interested in. So maybe you measure them at night and day. So there's, I guess maybe call that light level. So the same individual has measurements at night, and the same individual has measurements at day. Or you have any number of things that you can do to the same individual multiple times. So that within this individual, some class of observations are associated with one level of the covariates, and then another group of observations are associated with another level. I actually wanted to start calling this observation set so that I wouldn't inadvertently, as I just did, use the term group. But so it can be confusing and difficult to come up with consistent generalizable nomenclature. I also don't like how that there's a kind of asymmetry here between groups within individuals. So I'll talk about those. There's a third class where like observations can actually themselves be paired. So in the context of light, as I just described, where there's you collect a bunch of observations of the same individual, say in the morning, and a bunch of observations of the same individual at night. The morning ones you might treat like as I've described it, I haven't given you any information about what that collection of observations entails. So as I've described it, you could only assume that they're IID, identically independent, identically distributed. And so there's a bunch of observations at night and a bunch of observations at day, and they're both respectively IID. There is a way to talk about within individual manipulations that also have pairings at the observation level that you need to account for. I'm not going to talk about that in this case. An example of that would be like if you did this over many weeks and but just one observation in the morning, one observation at day, and you weren't looking at any kind of time series kind of reflection of weeks, but you did want the same day to be paired up. So the morning observation for this person in the morning and the evening for the evening to be paired up. You want them all to know that those two observations happen on the same day. And then so you have, for a given individual, a collection of pairings that kind of march along through time. I'm not going to talk about those as much. That tends to be a little bit rare because you can then just transform time into within an individual thing, and that's a little bit easier. There are some more niche circumstances where you do want this extra kind of observation level pairings or relationships, but we'll certainly talk today about the between groups and the within an individual, and you need to do something different for these two. Between groups is going to be exactly like we did at the very beginning when we were just talking about straight up regression. It's very simple, kind of plug and play, copy paste of what we did for regression in the non-hierarchical case to the hierarchical case. To deal with this within individual, we're going to be doing something slightly different, but also vaguely familiar. So let's go to this is the between. Yeah, so this is the kind of plug and play. Here I transitioned my code to just using the sufficient stat stuff. So I've kind of taken the collection of observations at the level of an individual and called that a cell, just in my code for naming. I jump around in terms of nomenclature on this stuff, and yeah, I think that's a reflection of how hard it is to come up with something that's generalizable. So you'll see that there's some number of cells, there's an observed for each cell, there's an observed mean, observed variance, and count of how many observations there are. There's also some sort of numeric, it's a categorical variable that's like an index, it's a cell ID. We're talking about individuals here, so we have some number of individuals. We're also talking about between groups predictors, so there's something saying how many between group predictors there are. I guess I could have started off like the earlier where it was a single predictor that was between group, but I wanted to show you the generalized version faster. And there's some number of combinations, so if you only had one between group predictor that had two levels, there's two combinations. If you had two between group predictor that each had two levels and they were you had data for all the combinations, there's four combinations. And though that like set of combinations of predictors and what the actual predictor is gets encoded as a matrix, just like we actually had in the the earliest multiple regression stuff. So I've named things slightly different in terms of what the indexes are named and what the actual variable is named, but it's the exact same overall structure in that you've got a matrix of predictors coming in. The extra is that we are associating each row in that matrix. Again, the columns are individual predictors, and the rows are unique combinations of that predictor. And I've added in this extra identifier that just gives basically a row number for each. It says for each individual in your study, so for each of these NID people, again, each individual person only experiences one particular combination of predictors. So it tells you what row in this matrix every individual is coming from. This technically isn't... there's ways to do this that don't require this indexing, but they then make you do redundant computation in the model. So I like this indexing version of things.
I don't know if you'll start losing.
Yes.
Can you zoom in?
Whole, yeah. Yeah, I don't respect the only 80 characters rule.
That's technically your phone.
Sorry?
That's like on your phone.
Well, I mean, it's generalized enough that it's in most IDEs now. But I think that conflicts with nice verbose variable names. I could split things onto separate lines, but that's even less standard. Anyway, same as before, I need to just pack the observed things that contribute to the sufficient normal likelihood into a single matrix. We're gonna, I think the way I did this was, why did I put it as eta? Oh, right, okay. Because we're doing sufficient, that's talking about wanting a variance as the thing, so since I was talking about variance anyway, I decided to use eta. Shouldn't be log. Okay. So eta is log variance, so it should be unbound. And I'm not modeling that. I'm not modeling the influence of the predictors on eta. No, I'm just saying fixed kind of thing. Actually, if I do this, is it going to give me a plot? It will if I source my R profile. And now, okay, I'll try, I guess, start that. I guess easier if I just go to the top of this and source this. Source that. And then find the check of this, place that in stand depth graph, and it needs the includes. There we go. All right, and if I zoom, it'll make it big. Okay, so I don't like the labels being off. I don't know. Labels bit. And I think I have to reopen this. Yeah, there we go. So yeah, we've got between group predictor, this matrix coming in. For each column in that predictor, we've got a coefficient reflecting what is the influence of that predictor. So those combine together to determine what the mean of that group is. So again, these are between group predictors. The predictors are determining, in this case, what the mean of each group is. People are going to vary within the group from one to another around that mean. So there's this other thing that's the standard deviation of the group. And I think the way I've done this is that the standard deviations are technically, the way I've done this is that the standard deviations are unpooled. So there's no hierarchical structure on these standard deviations. There we go. It's just there's a common prior, but there's no like extra hierarchical structure on the standard deviations. In theory, there's actually the same case with the means, but the means are directly connected to these predictors. You could actually have a scenario where you have a bunch of predictors and you kind of think that they're all going to act somewhat similarly, in which case you could actually pool these coefficients. You could say that most of these predictors should have about the same influence, and so you estimate out the mean influence and the standard deviation of influence. but we're not doing that. These coefficients are also fully unpooled. So we get out these means that imply the group, for each group, what the mean is for the group. We get out the standard deviations, which is the standard deviations for the groups. They're not related to any of the predictors. That then we do the standard non-centered parameterization, whereby we sample from a standard normal these random deviates for how each individual is deviating from their group mean, and then combine all of those together to get out for a given individual that is in a given group what their mean is going to be. And then we're, again, taking, I think I have a common eta that's just a single real. So log variance, it's got its own standard normal prior on it. But it's just a real. So everybody's got the same amount of measurement noise. And then the final, I think I showed you in the diagram that things combine, but to show you that they actually combine in the code. The means are determined by the predictor mats being multiplied, and it's a matrix multiply by the coefficient matrix. So this, the coefficient vector. And if I've got that right, it does matter like whether your coefficient, I'm pretty sure I got this right though, that the, if your matrix has the different, no, I don't. Unless I transposed. No. I think I need to have this as a row vector. Darn. I actually had a plan to actually test this, check this in real time, but we're running out. This goes to 430, does it?
Yep.
Okay, yeah, and there's a lot more interesting that I want to do. I might have these two backwards, or it might be that this needs to be a row vector and not a vector. That sort of thing I get wrong all the time, but it would actually throw an error when I run it with real data or with even synthetic data. Tomorrow you'll learn how to do the synthetic data, and that will be part of the Bayesian workflow part. But for now, let's just assume I got this right. So we get out the means by combining the coefficients associated with that imply the influence of each predictor with the matrix that describes what each group's predictors are. We then take each individual's, we get out what each individual's mean should be, given what their random deviate is, but then also what the mean for the group they are, so that's where that index comes in, and the standard deviation for the group that they are. We use that indexing there to get out for each individual what their unique mean should be given their group, and I guess their deviation, their mean, because it's on the basis of the group mean and the group standard deviation for the group they're in. And then finally, this last likelihood is the standard sufficient likelihood, where we're associating the row in actually this, as long as we have as many rows as there are cells. This might be a little bit redundant, but we can use this cell ID to just make sure that each of the observations line up with one person, and what kind of ID what group they're from. And the normal sufficient expects a variance as the second thing, so we just exponentiate our eta. I guess I could have had sigma and lower bound and a Weeble, and then just had a power to the power of 2 there as the argument. I think I did it this way because it's easier to then translate this into a location scale model if I wanted to. So that's group level predictors, very simple. There's no like correlations in the group level predictors. That's why I call them simple. You're not dealing with, you're just dealing with the introduction of a input data matrix of predictor values and a new parameter that's just the influence of those predictors. And you use a little bit of indexing to make sure that you're aligning everything with the right people in the right groups. Nope, that's an older one. Within, nope, that's an older one too. Okay, so within is a bit more complicated. And we're going to do it's what? Regression between. Did I just click the same one? Ah, there we go. A moment, it's bigger. Okay, so within is a bit different. We have a somewhat similar sort of structure up here. We're talking about a number of individuals. We have a number of kind of cells that reflect a collection of observations within a certain individual. We have a number of within individual predictors, and we have some sort of matrix that reflects for every cell and every within individual predictor what kind of the value is for that predictor. And then we have this other kind of indexing helper that tells us for each. Actually, no, this one is not useful because each individual, by definition, has every combination of the within predictors. So yeah, I left that in because I copied from one to another. But then we also have this standard input of the data in its sufficient format, which then gets combined together to a single thing. I think I had this in there, but I've discovered with this that that's not necessary to choose this transposition. I might just delete that. In terms of the new parameters, it's very similar, at least in fact, it's identical to the between in that I've added in a, oh, no, it's not identical. Before we had just a single new vector, which was the effect of the between predictors on the effect of the between predictors. Now we've got an effect of the between predictors on the mean, and then the kind of the across groups mean of the within predictors, and now we've got across group standard deviation of the within predictors. Let me actually run the model thing. And that's gonna within that transposed. Where's that? Because that's in dot product. All right. Okay, that passed. And if I stay today. No, what's happened there? Where am I missing a comma? Oh, slash, wrong slash. Yeah. Oh, there we go. And I'll zoom it. So we've got the same sort of scenario. We've got observations and a normal sufficient and the ID something going in there. But the ID coef, right, because we're combining the within predictors kind of at the to determine what the individual mean is. I could have had a derived variable. In fact, I might do that for simplicity here. And this should be. So the within predictor combines with the coefficients to determine for each individual, given that person's each level of the within predictor, what that predicts for the mean. Again, we could have done the exact same thing for their noise, their measurement noise, and had a location scale model. This is just a location model. I'm using columns dot product here, but think there's a matrix multiplication representation. Because but columns dot product is probably, that's why I had the transpose and everything, was because it was more straightforward to do this as a dot product of columns rather than a matrix, because we are actually dealing with two matrices. This ID coef is a matrix, and the input, the within predictor matrix is a matrix. So yeah, that I shouldn't have deleted that thing. In any event, if I had that there, it would have been a transpose, and that would have determined for each individual what their so we've determined at the group level what the coefficients are for across people. What is the mean influence of the within predictor? What is the variability from person to person in the influence of the within predictor? Because if we're talking about something like night versus day, like that as a predictor, and we've got the different people being measured at these different times, so we've got each individual being observed both at night and day. My kind of the influence of night and day on me might be different from the influence of night and day on another person and another person, so there's going to be variability in the magnitude of that influence, and so we need to have an overall, like across people, what is the mean of that influence, and what is the variability from person to person of that influence. So each individual has their own influence, and that forms a distribution across people that has a mean and a variability. So with the between, you only have what is the effect. Within, you have what is the mean effect across people and what is the variability in effect across people. So that's an extra kind of complication. As I've done it here, if I had multiple predictors in this matrix, they're all going to be considered independent of one another. So the influence of the effect, like if there were correlations, like if I had a night and day and another within predictor, let's say how much sleep I got the day before. You can imagine that the influence of night and day might be tied kind of in a causal way to the how much sleep I had, and so that there's a bigger difference in night and day on days that I didn't have sleep, and a smaller difference on days that I did. So there might be a correlation in the magnitude of the effects there. Actually, maybe I didn't choose an example that worked that way. But there is a lot of scenarios where you're within predictors. So in my world, I'm often doing cognitive batteries that are little video games, and we're measuring multiple things about the mind. And those things are being measured by manipulations that have multiple, like 2 levels. So I can operationalize one thing as like how much somebody responds to Stroop conflict and how much somebody responds to flanker conflict. But those 2 things, because it's all the same brain, and they're both executive function things, tend to be correlated with one another pretty strongly, but not perfectly. So they should be able to mutually inform, and this model doesn't have that mutual information. To do that, we've already talked about something that can do mutual information, which is a correlation, but I don't think I put that in there. So, oh yeah, I did. I just didn't name it differently. We just add in this Cholesky factor correlation, and we need as many kind of entries in this Cholesky factor correlation as we have predictors that we want to ask about being potentially correlated. But otherwise, we do the exact same as we had before. I've got some mic double check these because I didn't change this over to the ID coef gets simply matrix multiplied by this, and then we do a else multiply rep matrix and the SD and ID. Okay, so this goes back to what you remember seeing before. There's another way that actually the manual shows on how to do this kind of making something that has a mean across people, a standard deviation across people, plus a correlation across columns. But it uses something that I always get the order of whether I'm putting things in the right order wrong, whereas this other way I determined earlier today is not discernibly different in terms of performance and is harder to get wrong. So yeah, this is the way I suggest you do it. That doesn't involve the diag pre or post multiply. So this is very similar to what you already saw in terms of how to add in the piece of things are correlated. So we have got this new correlation thing. It's correlating the influence of the predictors within each individual, so that each individual has a individual amount of influence for each within predictor, but there might be correlation amongst those influences. And then the final thing is the exact same as the previous example, because we've already derived what this ID coef is. Ran out of time. There's so much that is. I mean, I feel like I've gotten through like some of the simplest levels of complexity you can start adding in, and justifications for adding in. Like you could, as I've shown here, we've made this just a purely location model. You could do all of this stuff to the scale part as well. This is starting to expand, like clearly the magnitude of the model, which is why I started getting into using these optimizations of doing the sufficient normal, and I skipped over some ways of doing things that didn't use indexing as I'm doing here that would have been slower, that in these bigger models would have caused problems. Hopefully I've given you at least some of the pieces to motivate appreciation that there's flexibility here to capture a lot more nuance than certainly the traditional non-hierarchical tools can achieve. One thing that I maybe want to clarify, I kind of previewed at the beginning that the proper application of a hierarchical model structure allows you to have more accurate capturing or inference on correlations. And it's actually this model that happens in. That is when you have a set of within predictors and you're trying to just ask how like correlated they are. In the psychology literature, there was some cool research showing like there was a bit of a scare where we thought that our measures weren't statistically reliable, but it turned out that people were doing the traditional non-hierarchical things, and when you can actually demonstrate when data is truly hierarchical and you fail to do this proper thing, that the correlations from one thing to a repeated evaluation of that same thing are biased towards zero. That it takes the data, it doesn't see by collapsing things to non-hierarchical, you're collapsing things to a mean, and you're not giving the model an appreciation for the magnitude of noise variability, and thus it thinks that that your measurement is perfect, and the noise variability it sees in the means is true variability versus variability plus uncertainty about the due to the influence of noise, and thus it discounts higher correlations to a greater degree than it actually should. It pulls the distribution of credibility down towards zero. So doing this proper thing allows you to see those correlations amongst your within predictors far more accurately, both precisely and accurately. It actually gets your posterior distributions are actually going to capture the true at a calibrated level. I guess the last thing, because I don't have a lot of time, is that I've used implicitly a multivariate normal correlation structure to capture the idea that things might mutually inform, they might be related. And by the way, you can totally just combine the previous model where it's a between group and as well as this within individual. So if you have between individual predictors and between group predictors and within individual predictors, you can easily just plug and play those two pieces. The one thing I wanted to caution about is that be careful when you get lots of within individual predictors trusting the multivariate normal, because the multivariate normal is actually a very specific kind of structure. It's kind of like your priors. The priors imply a very specific set of predictions for what it can generate as data, and the multivariate normal assumes that the data is genuinely multivariate normal, whereas a lot of people treat it, including myself at one point before I discovered this, that it's a general catch-all for any possible combination of relationships. And I discovered this in the context of talking about a scenario where I expected some predictors to be highly correlated and others I had no strong expectations. And in my priors, I thought I put a flat prior on things, and I thought, hey, it's going to catch the highly correlated things, it's not going to catch the low correlated. And that would work if I actually just had the highly correlated things in there, or if I just split it out to the uncorrelated things. It would catch the high correlated things in the high correlated only context and the no correlation in the low correlation expectation context. But if I had them all combined, that's not consistent with a multivariate normal. You have to actually piece together the relationships in a much more kind of manual way. And that's where I've started getting into representations of hierarchical models as structural equation models. And that's where it's the same general like code, but you have, instead of using like this, okay, I'm just going to do this multiplication to achieve this correlation amongst this matrix of vectors, you actually construct the vectors in a sequential order and have variables that directly encode the correlation. And you have to be much more careful about the, you end up having to bring to the table more prior expertise on what that structure is, but it ends up being more flexible than the multivariate normal for those cases where multivariate normal actually imposes too much of a constraint that conflicts with your expertise. Any general questions or? Well, I'm going to I'll provide the recording of this to the conference team, and I'll certainly provide the link to all this code and everything on my GitHub. So you'll have access to all this stuff, and I certainly am on the discourse forums and available to provide input on hierarchical things. One thing I didn't cover that I just want to talk is that it's really great to do joint models when you have different kinds of measures from the same person. That one is a Gaussian, another is a binomial, another is a Likert, or a ordinal variable. It's really easy to add those pieces in at the likelihood level and have kind of common mutual information up in the higher levels of the hierarchy. And the last thing, actually, somebody asked at the break that I wanted to get to is that so far I've been talking about just single hierarchical trees, things are kind of coming down from these branches all to one thing, but there's actually possibilities for multiple trees then combine only last at the observations. So that's very common in the psycholinguistics world, where we have individuals as kind of clear identifiable things than which we want to group, but then we're using stimuli that are words that also have the same sort of complexity in terms of their influence on behavior as as people might have in terms of variability from one to another. So that's a world where they learned to do crossed hierarchical models. And those are ones where you can't use the normal sufficient trick at all, because it's right at the level of the likelihood that they combine. But that's also, a cool world to play with in terms of hierarchical structures. All right, well, thanks for your attention.